Greetings from social isolation. My name is Jonathan Wise. I'm the VP of Technology here at CESMII and the architect for the Smart Manufacturing Innovation Platform that we've been working on. This presentation was destined for our annual meeting, an event we were all looking forward to. Things have changed significantly in the world since then, but we're glad that technology gives us opportunity to share with you what we've been working on, and we hope that you'll continue to provide us with feedback in the form of questions or guidance or ideas that we should be thinking of as this platform evolves. I'm going to start today with a few slides leading up to the demonstration of the progress we've made in the platform over the past couple months. I think they're necessary just to discuss a couple concepts and themes that have been guiding our work as we've been progressing. But the bulk of the time today is going to be with the broader demo team, CESMII members and industry leaders who share this vision and have led their efforts over the past couple weeks to put together a demonstration of the current state of the platform.
This is my picture of pilot Purgatory. This is what the manufacturing software landscape kind of looks like to me. We see a lot of abandoned trees, a little bit of value growing out of some of them, but in general, this is a pretty bleak landscape. It doesn't have to be this way. In automation world, just this past February, Stephanie Neal had a great quote, kind of pinpointing what we wholeheartedly agree that we need, an unobstructed way to move information. And you could make the argument that we have lots of ways of moving information, but the point that I think Stephanie's trying to make and that we agree with is that there are too many different ways to do that. Too many vendor-specific approaches to solving the same problems over and over again. And what that does to us at kind of an innovation level is it forces us to make difficult and often unrepeatable implementation decisions based on a particular scenario. To solve a problem against one vendor's technology stack is to force me to solve it again on another stack. You've seen this slide from us a couple times over the past couple months. And I think it does a good job, even though it's sort of a marketing level slide, of identifying the three levels that we are focused on down the middle there. And on the right, some of the ideas that we've been pursuing to solve some of those problems. So those three levels are important. We're going to talk about them a lot because in each of them, I think there's a representative problem that needs to be addressed. And what I want to call out is that it's not CESMII's intent to solve them once and for all, rather to provide mechanisms by which all of us can solve all of these problems. And that's a pretty lofty goal. But before we go into kind of our approach, I'd like to spend just a couple minutes talking about those representative problems at these three levels. So at the first level, the problem, in my opinion, is interface anarchy. At the level that we call the edge or the connector, the ingestion point of data, there's so many different things to talk to. Generally, we've agreed on a physical interface, looks like an Ethernet cable in most scenarios, often a high quality or rugged Ethernet cable, but the physical connection is the same for most information sources. There are some that require a different kind of connection, but even then the implementation looks a lot like Ethernet. A standard has emerged at the physical level. At the interface level, the protocol my software needs to speak to get data, there are hundreds of different protocols. Each of them evolved from a different place, each of them well-intentioned, and each of them has specific use cases. But none of those good points change the fact that there are many of them. One of those protocols is OPC-DA, the original OPC specification that was designed with the intent of solving this problem. OPC-DA was an important step in the right direction in the 90s. And as it's evolved towards OPC-UA, it's begun to solve some of the problems that kind of remain with that legacy. Classic OPC depends on binary communication and Windows technology called DCOM that is rapidly fading away. So OPC UA solves those problems, and it solves additional problems. And it's one of the reasons that I've kind of given it a gold star here, is I think it's the best chance that we have as an industry of kind of rallying around a common interface, even if that leaves us adapting to other interfaces down at more primitive levels of comms. So problem number one, too many interfaces. We need to come together and solve that. CESMII is 100% on board with that goal, and we are extending the OPC UA specification to help solve this problem in what we think is a more distributable fashion. Problem number two may require a software developer's perspective. I like to call this Jonathan's theory of alternate evolution. If we begin kind of going back in time to, let's say, the VAX as the beginning of computer technology in a form that we could apply to many of the problems of today, technology evolved, at least from our perspective, in sort of two different directions. Information technology evolved towards object-oriented programming, strongly typed objects that are representative of data. We've abstracted those objects from the data, bound it to that data, and then we built our applications on top of these objects. Those objects inherit from other types of objects. So as a software developer, things that I can learn from one set of objects can be applied to those that inherit from it. Object-oriented programming is a powerful set of principles that are sort of table stakes in software development. In fact, we've moved beyond that now in the IT world, and we have sort of post-OOP ideas that we're exploring. But we still consider an object-style interface to be kind of a minimum bar for most software development. In manufacturing technology, we evolved in a very different direction. We evolved from electrical diagrams, which makes a ton of sense because these are electromechanical systems that we're controlling. And so that skill set is also a logical skill set. It has much in common with software development, but the minimum bar there looks more like key value pairs. The most mature structure that I can depend on is a label and a value sampled over time. So in the 90s and 2000s, we applied software truism. Any technology problem can be solved with another layer of abstraction. So we introduced multiple layers of abstraction. Vendor-specific object models that were constructed and applied after the fact. You brought in a vendor technology to make sense of the OT technology, to re-represent the data that's in the systems as objects so it could be exposed to traditional software development. I am a part of that legacy. I worked on many of those systems, and it was a good idea. It was a good way in the 90s to accelerate software development. But it has a couple inherent problems that maybe we didn't realize at the time. One is this vendor specificity. The object model is in fact an API. So I, as a software developer, have to choose the API that I want to depend on. And that forces me into a fractured ecosystem where my solutions aren't easily repeatable across different vendor APIs. The second, I think, is equally significant, and that's the fact that these object models were after the fact. Built by a system integrator or by an end customer, they were built to attempt to reflect the understood or observable structure in the manufacturing system. They were not built with the manufacturing system. Now that's changed in later years, but only through discipline, not because in general the tools require it, but it was understood to be a good practice. But that practice, again, was applied in a vendor-specific fashion, which made the repeatability of the outcome hard to reproduce in another vendor's ecosystem. So that's problem number two. Problem number three, we created as an attempt to make an end run around this. We looked at the technology that it was evolving for analyzing business systems or human sentiment. And we imagined that we could easily apply that to manufacturing data. I call this the big data myth. It's not that I'm not a believer in analytics or in machine learning or in storing large amounts of data so we can get value out of it. I think the underlying assumption, in fact, I know the underlying assumption for most machine learning algorithms is that there's going to be good labeled data. We call this features, and the features are used to train the algorithm. In manufacturing, because we're going back either to a proprietary object model where the feature labels are arbitrary and assigned independent of the original creation of the system, or worse, we're going around that curation and we're going directly to the data source, we end up with features like T_01-4. And it's impossible for a machine learning algorithm to intuit that that label means the temperature on a paper converting machine at a particular piece of equipment in a particular facility in Alabama. It can't be drawn out of that label. The label is not useful. We need context before we store this data. We need that context to be accurate at the source, not imposed after the fact. If 70% of data science is cleansing and preparing the data, that 70% can take years in a manufacturing system. We have to do better. Before we can harness these tools properly, we have to have a platform that exposes the data in a way that is meaningful and useful. So those are some of our goals, and granted, they're lofty goals, but we are not doing this alone. We are doing this with the vendors and the organizations that have been trying to solve these problems for years. And I think it's working together that is going to make the difference here. Moving away from a proprietary approach and to an open specification that everyone can embrace and guide and adopt can help us solve those problems. So our agenda today, we just looked at our current state. I'd like to show a glimpse of what we think is a possible future, and then walk through the steps that we've taken recently to get us there, and introduce you to some of the helpers who have been working with CESMII along this journey.
Hi, I'm Tara. My company, Genco, makes the best apple juice you've ever tasted. An important part of ensuring our quality is our reverse osmosis system. This skid contains everything we need to clean the water going into our product, removing unwanted particles by pushing fluid through a filter. Part of that system is a membrane that needs to be periodically replaced to ensure the filter is working optimally. Up until now, we've scheduled the replacement of these filters, but occasionally spot tests in the lab find quality problems that force us to replace the filters more frequently than scheduled. It would be better if we could detect a problem and proactively replace the membranes based on actual usage. I wonder if someone else has solved this problem. I know! I'm going to check the CESMII marketplace. Sure enough, it looks like there's already an app out there that does exactly what I need. Let's go through the steps to install it. I don't have the Smart Manufacturing Innovation Platform installed, but I do have my manufacturing data collected in an OSI PyHistorian. So, I'll start by creating my own innovation platform instance. Filling out this form registers me as the administrator of the instance, but I'll be able to grant access to others in my organization as well. I can see that it takes a few minutes to create the necessary resources in the cloud that are specifically registered to me. I'll get an email when it's done. Looks like it's ready. Now, I need to connect my on-prem data source to my innovation platform by installing the connector on a computer inside my network. This computer needs to be able to reach both my PyHistorian and the internet, so I'll work with my IT department to establish a DMZ. Fortunately, the data is encrypted with a two-way certificate, and the connection is outbound only, the innovation platform never needs to reach into my network. The final thing I need to do is install the predictive maintenance application. The app itself lives in the cloud, so I won't need to do any more on-prem installation. But I will need to grant the app some permissions. First, the app needs to create a profile in my innovation platform called Reverse Osmosis SKID. Well, that makes sense. Next, the app wants permission to read data from my system. Finally, the app wants permission to write to, or change, objects from the profile it created. This looks good to me, so I'll approve. Now, the innovation platform goes to work doing a bunch of automatic steps to get the app ready for me. The necessary cloud resources for the app are started for my company. The connector receives a copy of the profile and starts trying to find the data for my system. If it can't find the data, I'll answer some questions to help make the right connections. Then, the connector begins delivering the data to the innovation platform, so the app can start its analysis. And in a few minutes, the app is up and running. I can navigate to it right from within my innovation platform and see the analysis being performed. That was pretty easy. The marketplace made it simple to find a pre-built solution to my problem, while the profile allowed that app to be built in a way that was independent of my particular infrastructure. The innovation platform made it all work together with a single, secure outbound data connection that I'm always in control of. Now that is smart manufacturing.
So that video is a picture of one potential end state that we want to get to, where a solution can be easily acquired and applied to a system. And this landscape here is our current state. How do we get from one place to another? Well, I'd like to introduce you to my happy tree. If those are what dead trees look like, this is what I think a healthy tree looks like. And I'm going to invite a friend to help introduce some of the parts of this healthy tree. We'll start with the roots. The roots of a healthy system are the operational network and the devices within it. And I say healthy because we need to connect to these in healthy ways. We can't build a connector that places so much burden on the OT system that it can't keep up with critical operational decisions. We have to have a low impact way to draw data out. That mechanism needs to be secure. It needs to not interfere with the operation, and it needs to speak many languages. It needs to be able to adapt to all of these protocols so that we don't have to implement multiple connections there. That connector, that piece of technology that holds the translator to all these different languages, we'll place that at the edge. We call it the connector. The edge passes data to the core platform, which prepares that data. It traps the context, it applies structure, it builds an object model out of the data so that it can be exposed through the branches to the API and the workflow that give access to and orchestrate the different systems that need access to that data. And finally, the healthy fruit from this tree, the bloom that we want to see is many apps, a vibrant ecosystem of apps growing out of this platform where lots of different problems can be solved. If that's a happy tree, it starts with a good seed. And we think that seed is the smart manufacturing profile. The smart manufacturing profile is used at every point in the tree. It brings life to our healthy ecosystem. If these are the three kind of main parts of that architecture that we looked at earlier, the edge, which gathers the raw data, the core services, the data and object model where context is stored and related, and then the apps are the consumers of that structure, then the profile is used at every level to determine, first, what data to collect and how. Second, what the object model looks like, what structure to impose on the data. And third, the interface that is exposed to the applications that allows them to focus on the value they're trying to create. Application developers shouldn't have to focus on getting access to and contextualizing data, they should be able to take that for granted. The profile then becomes the contract that an application developer can rely on so they can focus on the problem they're trying to solve. Profiles are not wholly our invention. Profiles are an extension to the OPC UA information model specification to allow those information models to be encapsulated, distributed, fetched on demand from a marketplace, and applied live to the manufacturing system, to the OT system, and to an instance of the platform that a particular user is connected to. So if those are the ideas, and if at this point they seem a little abstract, what I hope we can do today with our demo is walk through an application of these ideas that's still early state, but begins to exercise each of these concepts at each level, and hopefully demonstrates that it is easier and faster now to connect apps that provide value to a manufacturing system. I'm excited because our demo today, unlike our previous demo, which is built from simulated data, this demo is built against a real manufacturing system. Our first Smart Manufacturing Innovation Center, North Carolina State University, came online over the course of just a couple weeks, connecting with the Edge connector, passing data to the core, and beginning to connect to apps that had access to that data in a rapid fashion. NC State has some first-class facilities, and it was a real privilege to begin to explore these ideas and implement this technology against those systems. And I wanted to invite one of the key contributors to that implementation, Tim Shope from Avid. Avid Solutions is a systems integrator that shares our vision and our passion for repeatable solutions, structured data, and bringing new value to manufacturers. So Tim, would you walk us through the facility and tell us a little bit about the project?
Hi, I'm Tim Shope with Avid Solutions. I'm here to tell you a little bit about the things we've been able to do at North Carolina State with the CESMII platform to date. Most of the work that we've accomplished so far has been around the BTEC or the biomanufacturing facility there at NC State. The architecture that is installed there is an ABB, DCS, as well as a Delta V platform, and an OSI Pi system. We were able to get the OSI Pi system outbound and ingesting data into the CESMII platform, into ThinkIQ, and we also were able to install an on-prem Seek analytic engine to do some basic analysis on the reverse osmosis filters. In addition to that, we connected a IoT sensor to monitor the condition and health of one of their critical assets. So we'll go through those two scenarios in a little bit of detail. The first is the reverse osmosis filter. We built a basic analysis leveraging the historical data in OSI Pi and basically create a capsule for when the differential pressure goes up across the membrane, and basically set a flag via the GraphQL API ingestion into the CESMII platform that furthermore downstream through Savin kicks off a workflow to get the membranes replaced and get the reverse osmosis filter back in operation. The other application that we did there was around this circulation pump. It is a continuous running variable speed drive that circulates high purity water that is leveraged in a number of different things in the facility. Just to show you the criticality of this pump, there's actually a spare pump that sits in the floor right beside it all the time so that they can basically provide a Winston Cup pit crew change if something were to happen to the pump. What we installed there is actually a Semiotic Labs data acquisition device that has an uplink to the cloud, and it's basically an IoT sensor application that monitors the current and voltage going to the motor, does some waveform analysis, and can basically set conditions whether the asset is working normally, if it's detected any kind of bearing issue or anything. So it's a predictive condition-based monitoring of that asset. But the really cool thing is, even though this is just a third-party IoT device, we're able to ingest this data not only the conditions, but the real-time performance data directly into the CESMII platform so that we can do incremental condition-based analysis and kick off workflows for getting repair of the pump if needed.
Thanks, Tim. So that's the physical operation that we want to draw data from. But in order to get data into the CESMII innovation platform, we need to define a structure that data will live in. This is a programming concept called an object model, and it's a fairly common one in the world outside of manufacturing. But in our space, we've never really arrived at a standard to do this. What we're proposing in partnership with the OPC Foundation is that we build these structures as type definitions or smart manufacturing profiles that can be built once and distributed via a marketplace so many people can benefit from them. The tools that we have in place today to build those are built right into the platform. And I've invited Doug Lawson. He's a board member here at CESMII. He's also the CEO of ThinkIQ, contributing member to technology in the platform, to walk us through the process of building the model of this physical operation so that we can map our data to it. Doug?
Thank you, Jonathan. It's really great to be able to show the platform and how far it's moved since our original community technology preview. What you're going to see in this demonstration today is the platform at the center of the entire demo. So all data is going to flow through the platform to the applications. Data is going to be written back into the platform and exchanged through the platform. To get all of that to work, the first thing that we needed to do, Tim and his team created the physical model that represents the BTEC facility. So this is the physical equipment in the water purification side of the plant, and it's creating high purity water. If we want to look and see the data, for example, on this high purity water distribution tank, we can simply go in and say, show me the trend of that data. I'm going to open it in a new tab so that we can easily go back to that process diagram. And it's gone away and it's fetched the last hour of data for me for all of the tags or attributes that are defined on this tank. So we can see that the tank has flows, pressures, conductivities, and the kind of things that you would typically expect to see on a physical piece of equipment. And you can also see that we have equipment stored for long periods of time that we can get to at very high performance, stored in the cloud. So we now have the ability to get data from virtually any on-premise historian. We can get it at full resolution, take the data, push it up into the cloud, and to be able to do any kind of analytics and contextualization of the data in a secure manner in the cloud. So how do we physically do this? The most important thing is to be able to model. Models is really the ability to create what we will eventually have called profiles. And when we create something like that high purity water distribution tank, what we do is we define attributes on it that we map to physical tags from external systems or configure and map to calculations or definitions. Our ability to do that is predicated on the assumption that we can create types. So I define a distribution tank once, which was used in that example. And then for every one of my tanks in the system, I can go ahead and do that. So here's an equipment type. And if we look, we'll see the attributes are defined here. They're not wired to tags at this point. And we've got the ability in the new version of the model to do much more sophisticated types of attributes. So these attributes can now be configuration things that might be the purchase date, the capacity of the tank, or any other relatively static information. We can wire tags or attributes to external tags, and we can wire them to internal tags that come from calculations or manual data entry or from other places in the model. So a lot more sophistication in terms of the things we can do with the basic attribute types. And that includes the ability to map things to attributes that are shared in definition between equipment types, which can be very powerful for certain types of modeling. We can also, in the equipment type environment, for the first time, we can create composite types. So this batch tank that we're looking at over here contains inside it an inlet valve and two other valves. Perhaps a more familiar example of that would be if I wanted to create a vehicle, I could say I want to create an equipment type called car, which derives from vehicle. And then I would say the things that make up the car are the engine and 5 wheels, front, left, right, rear, and the spare. And each wheel contains a tire. And each tire has a rated pressure of 35 pounds per square inch and a measured pressure that's wired to the equipment or sensors on the physical car. So the modeling capability is greatly improved. That includes the ability now to define for any attribute the engineering unit, to map that back to the underlying quantity kind, and the ability for the system to automatically convert values backwards and forwards. That's not just for the purposes of display, but if I define a calculation that's calculating, for example, the inferred energy on a pump, and one of my pumps is specified in pounds per square inch, the other one is specified in bar, my calculation will automatically convert that to the underlying common unit of measure, Pascal, and take that and push that result once the calculation is done and return it back in the desired engineering unit. This greatly reduces the complexity of building complicated systems. And then finally, I'd like to very briefly show the part of the system that's really critical is that we've added in this new capability in the system to be able to look at anything that's in the model and to be able to get the data through this new API called GraphQL. Now, GraphQL is a broadly adopted standard in the industry, and it's really directed SYSMII spending that has taken us and said, we'll get rid of the custom ThinkIQ API that we used to provide. And now everything that you're going to see in this demonstration today, where our applications exchange data with the model and with one another, is all being done for this new standards-based GraphQL. So Jonathan, that's about as much as I can cover in a very short period of time. I'm really excited as to where we are, and back to you. Thank you.
Thanks, Doug. So those concepts you covered, type inheritance and relationship between objects in a way that forms a graph, these are the kinds of things that software developers have come to expect in an application programming interface. So one of the things that we wanted to demonstrate today is that the model that we've built of the facility is automatically reflected into the API, and it allows applications to easily get access to and update the data in the platform. To show us this, Avid has integrated the application Seek into our new graph-based API. They're consuming data from the platform, using it to perform analysis in this external tool, but then returning the results immediately back to the platform so that we can react to it. I've asked Nate to walk us through what he built in Seek.
Hi everyone. Here in our Seek dashboard, we have two different signals coming from our RO filtration skid. One of them is the outlet pressure, and one of them is the inlet pressure. These two calculations will give us the differential pressure between our membranes, which gives us an accurate depiction of how well our RO skid is functioning. Fortunately, we don't have a signal that calculates that directly. So what we're going to do is we're going to create one of these signals using the Seek tools. To do that, we go to Tools, Overview, and Formula. And to as simple as using the Seek conditions, or the Seek syntax, rather, and calculating the inlet pressure, which should be higher, and subtracting that from the outlet pressure. When we execute this, we get a signal that looks very similar. That records the differential pressure over time. Now, we can use this new signal to try to set up conditions to know when our RO system might be running into issues. So the first thing that we're going to do is we're going to create a scorecard metric. This will give us a graphical display of when our system starts going out of spec. So we'll call this RO alarm scorecard. We're going to set the item to measure to be Formula 11. And actually, I'm going to go back and edit this and call this RO DP. So now when we go and create our scorecard metric, call this RO DP scorecard. We're going to select an item to measure, RODP. We're going to add thresholds. So we're going to set a high threshold to be about 35 psi. We're going to add another one for our high to be 25. We're going to set another high to be 15. When we execute this, you can see on our screen, we get a signal that shows our scorecard. Now what we're going to do is we're going to create capsules that will send an alert to a different system whenever we start going out of spec. So when we execute this, we can see down in the capsule pane here, it's calculating if we have any situations with this condition occurring. So here we can see we ran into this issue. And if we scroll over using the backwards or forward function, we can see this whole time we're above our 35 psi threshold. So in our situation, we are sending this signal directly over to Savagent, where they run a workflow based off this condition.
So what we've seen so far is the data is flowing out of the operation into the structures that are enforced by the platform and then made available in that same structure to applications to interact with. We've introduced an application, Seek, that is consuming that data and analyzing it, and it spotted a problem in side A of our reverse osmosis skid. We can see that from the trend here that the external application has injected an event, and the rest of the platform, all other constituents of the platform, are able to consume that event using the same API. What we've decided to do in this case is connect a workflow that's watching for that event, and it's going to lead both platform systems and people processes through the steps that need to be taken to remediate this problem. To do this, I've asked Mark Besser, he's a Senior Vice President of Customer Success at Savagent and a member of CESMII, to walk us through the workflow tools and the particular workflow that's going to help us address this problem in the operation. Mark?
Thank you, Jonathan. For those of you who do not know Savagent software, we are a work automation platform that's really anchored by 4 pillars. One is a IIoT asset connectivity engine, tying into sensors, PLCs, machines, systems, applications, databases, people, really any data producer, all to get data mobilized. We have a data historian for storage and analytics. We've got an event detection engine, watching and listening for things that are happening inside our plant. And we've got an industrial grade workflow work automation platform. Today's emphasis is really on orchestration, which is a common use case for Savagent. This demo, which you'll see, is, I think, similar to really any other company. There have been investments made and solutions in place to manage all aspects of the business, from sales to finance to HR to manufacturing to supply chain functions. In addition to technology and systems, we also have internal and external humans producing and consuming data, all to keep the important operations running. So how do we stitch all this together in a way so the collective whole is smarter than the sum of the parts? That's really the orchestration power of the smart manufacturing platform. In our example, in the upper left, we've got the start of the workflow. It's where the anomaly was triggered by Seek, initiating the remediation work. When you view workflow execution in this execution engine, as data and actions flow through the workflow, you can actually see the decisions being made, which are determining the next steps and next activities. And you can actually follow along the execution path, which ultimately gets highlighted in red. In our demo today, we've been alerted to this anomaly with the data in the manufacturing process that requires further attention. Seek has let us know that we have a membrane problem, so workflow springing into action. It's going to further recognize the type of that event or the issue, determine the course of necessary action, and direct data between the producers and the consumers and the actions with the systems of record, passing all that important information and context to those systems to facilitate the needed activities. With the issue coming from Seek, our first action is to interact with the operator to get confirmation that what we think has happened actually did happen. As a side note, in a lights out factory, this confirmation step is really not necessary. The platform can actually automatically detect and determine and remediate any issues without human involvement. But now that we received our confirmation from the operator acknowledging the issue, what's next? A couple of things. We branch out simultaneously to launch into two separate work streams. One, we're interacting directly with the maintenance system to put them on alert, open a work order, dispatch a mechanic to fix the membrane problem, get the line back operational. We're passing important information to them automatically. The type of the problem, what needs to be fixed, the severity of the issue, etc. So you can see workflow actually initiating the work order as part of the demo process. Simultaneously, we also need to reach out to our enterprise software system, SYSPRO, and to allow them to facilitate the impact to schedule and plan. With that, I'm going to hand off control to Lynette. Lynette is a senior product solution engineer at SYSPRO, and she'll take it from here.
Thanks, Mark. Just a little bit about SYSPRO. SYSPRO is an industry-built enterprise resource planning solution, and it's designed to simplify the complexity of manufacturers and distributors. SYSPRO understands how manufacturing and distribution businesses operate and compete, whether it's rolling out new technology or striving to optimize existing business processes. We value our relationships with our customers, partners, and employees, and above all else, strive on a daily basis to deliver operational value to our customers around the world. Now, the CESMII platform itself has detected an issue in the production process, and the workflow has requested the job be placed on hold while we further investigate the problem. So our production manager logs in, and he will be receiving a notification that something's happened that he needs to take action on. Right from our dashboard, we can click in and we can be taken right to the job. The actual workflow has put the job on hold, so we're aware of what the issue is. And right from there, we can also see that we have a problem with our filtration system.
Thanks, Lynette. As we return to the workflow, having acknowledged the change in the business systems, we're now going to move on with the remediation steps. At this point, we've probably identified the immediate problem, but we need to do further analysis to understand the downstream impact of this event. To do that, we're going to use the model that the platform has of the operation and the relationships between the objects in that model. And we're going to combine that with a unique application of the platform called material flow. I've invited Doug to come back up and walk us through that set of tools.
Thank you, Jonathan. So now we've seen the anomaly was detected. It was passed off to Savigent where a workflow was ran. That workflow eventually called back into the platform and flagged the platform with the fact that a contamination event likely occurred. So this is where the ThinkIQ software picks up. Now, what is ThinkIQ? ThinkIQ is one of the vendors that has contributed significantly to the platform. And we are a company that really specializes in trying to provide end-to-end visibility across a value chain, across a manufacturing value chain. So, for example, in food and beverage, that might mean that we provide full visibility into the provenance from farm to fork. And we provide the ability to optimize that entire value chain. So how do we do that? Here we look at Acme, and as I said at the beginning of the presentation, we've taken the liberty here of imagining Acme, a company that takes the pharmaceutical product from biotech and turns it into pills. So it's a process of mixing it with sweetener and flavorant and colorant, and then it coats it and turns it into physical pills, and then puts it into packaging. So a very typical process. We've shown here a highly simplified version of that process. Here we have the color and flavor batch tank. It receives material from the color tank and from the flavor tank, and it does a processing on that material. So if we go and look at the trend data coming from that, and I'm going to zoom in just a little bit here so we can see the data more clearly, we see a very typical pattern of a batch tank. So we see that the level rises, or the weight in this case rises. It rises in two distinct steps. Here the tank is being heated and then filled and then agitated. And then the green line that we see is the outlet valve opening and closing, and we see the level of the tank slowly descend back down until it's empty in a series of steps. As humans, as engineers, we can look at this pattern and we know exactly what's going on. If we look a little bit further down the process, the color and flavor batch tank feeds its material to the use tank. And if we look at the trend in the use tank, we see a very different pattern. So in this particular case, the use tank has material flowing in and out at the same time. And we see this much less clear pattern where we see that, first of all, the tank doesn't always empty. It only becomes empty over here. And then we see that it's filling and emptying at the same time. And the blue line is telling us when the output valve opens and closes, a much more complicated pattern. As all of you are probably aware, it's very unlikely in a manufacturing system that the control system will tell us exactly how much material and what material moved from each piece of equipment to another. That's not typically what control systems were designed to do. So if we go back to our colored food tank and we say, how does the ThinkIQ look at this problem? We now get an entirely different view into the data. So ThinkIQ has algorithms that run constantly in real time. And we look at all of the typical manufacturing operations: filling and emptying, blending and merging, assembling and disassembling, splicing, all of the typical things that we can detect by looking at the existing sensors that were put in for the purposes of control, and then show you the data in a fundamentally different way. So what are we looking at here? We're looking at the color and flavor batch tank, and we're seeing where the data came from. If we go backwards in time a little bit, we can see that each time the tank filled or emptied, materials came from different places. So here, in this movement, the material was coming into the color and flavor batch tank from the color tank. Over here, in this movement, we see that the material was coming in from both the color and the flavor tank, 30 and 70 kilograms of each, and that from there, in 5 discrete movements, the material flowed to the use tank. And I can navigate to the right and I can see where did those materials end up. And in a full-grown process, I would be able to go all the way out to the finished goods and all the way back to the origin of the materials. So what are we looking at over here? This information over here is colored in red, and this is the point at which Savagent came back and said, you've got contamination. And the ThinkIQ system looked and said, well, I've got contamination, and everything that was produced here, 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 and here is contaminated. Or looking at it where it actually ended up from machinery, everything that went from the color and flavor batch tank through these transactions to these places, and we can follow it all the way through the process, is the material that needs to be pulled back. And we detect that instantly and in real time, which is an incredibly powerful mechanism. So how did the system detect that? It looked at the same sensor data that I was showing you a little bit earlier, but here the results of that detection are. So the system tells us that it was looking at what allowed it to see those movements was the inlet valve, the outlet valve, and the material dwell time. And this is what it saw for those patterns. So the blue data is where it said, I've detected an inlet, and you can see those inlets here and here. And the orangey brown colors that you see here is where it said, and this is where I saw the outflows. And here they are, here and here and here and here. This data is foundational to being able to optimize any manufacturing value chain. If you can't know with high granularity how events occurred and how things relate to one another, it is truly impossible to find complicated cause and effects in a typical manufacturing network. And that is the fundamental building block of the ThinkIQ software, which runs on top of the platform. Jonathan, thanks for the chance to show a little bit of ThinkIQ. Back to you.
Thanks, Doug, and the rest of the demo team. Today, we saw data flowing from a real manufacturing operation into a strongly typed model where objects in that model have rich relationships with each other. We've seen an API that reflects that model out to application developers. We've seen an app interacting with the model
updating the data that's in the platform, then using that external analysis to trigger an orchestration through workflow that allows us to interact with business and maintenance systems to solve a problem. And finally, we've returned to the material flow application to understand the scope of this problem as it flowed through our process. It's important to understand that we're not building this alone. We're benefiting from the work of other organizations that have proposed standards in this space. One of those organizations is the OPC Foundation. The SM profile, the type definition that we use to enforce structure on the objects in the model, comes from the OPC UA information model specification. We want to take that spec and we want to extend it through a companion specification to allow for distribution and reapplication of profiles across all instances of the platform. Another OPC Foundation member is Microsoft, who's provided much of the infrastructure for the platform today, and it's been contributing to these open standards. The platform itself is agnostic. It can run on any cloud provider, but Microsoft's contributions have really accelerated these efforts. That said, we all believe in open standards, and to drive that point home, we want to show just one more app that's built on the platform that happens to be running on AWS, but it's interacting with the platform via these open specifications to solve another manufacturing problem. So I'm going to invite Tim back up to show us one more application running external to the platform, but benefiting from these open specifications. Tim?
Thank you, Jonathan. What I'm showing you here is the web interface for the IoT sensor from Semiotic Labs, which is called SAM4. It creates a dashboard of the recirculating pump for the high purity water that we talked about earlier. As you can see, it's pulling power, current, voltage, power factor. It keeps up with runtime, energy consumption, number of starts, etc. And this is all really powerful data, but it is still kind of in a standalone application at this point. So what we did is we leveraged Azure Functions and GraphQL to be able to bring this data into the equipment model that Jonathan and others have been showing you. And so this is the distribution pump. And so we can look at the equipment detail for that, and you can see that we're bringing that same current and energy and voltage in, but there's another variable here, which is pump speed, which is actually coming in through the OSI Pi ingestion from the ABB DCS. So we're able to now historize in the cloud, trend. We could bring this back into a number of analytic functions to where we can show data ingestion from multiple different streams and look at a holistic asset monitoring perspective. Back to you, Jonathan.
Thanks, Tim. It's awesome to see these disparate data sources running on other infrastructure coalesce into a common platform by embracing these open specifications. We've covered a lot of ground here today. A lot of software was shown. Some new concepts were introduced. If this seems overwhelming, if this seems out of the reach of small or medium manufacturers, we want you to know that all the members of CESMII have a passion for making this technology accessible. And to demonstrate that, I want to introduce just one more presenter, someone I'm really proud of. My 13-year-old son has built a parallel project. While we were working on connecting this enterprise software, he was working with a $30 Raspberry Pi and a $6 sensor kit to connect our fridge at home into the Smart Manufacturing Innovation Platform.
My name is Benjamin Wise. I'm 13 and I want to be an engineer when I grow up. This is a Raspberry Pi Zero. It's a tiny computer that you can program to do just about whatever you want. This is an environmental sensor. It senses temperature, humidity, and air pressure. The fridge sensor that we made senses environmental conditions on the inside of the fridge. This is the Raspberry Pi Zero. This light indicates that it's working. This tells you whether the fridge is opened or closed. And these lead to the environmental sensor on the inside, reading temperature, humidity, and air pressure. The Raspberry Pi collects all the data and sends it into the cloud where you can access it with your computer. When the fridge door was closed, all of the environmental conditions remained steady. But when it was opened, there was small change in temperature, but huge change in humidity almost instantly. And then it took a long time to recover. This project only cost about $40 and took a few weekends. It was really fun. If we can do it, so can you.